At the end of this video, you should be able to define molecule and molecular formula, explain the relationships among potential energy, distance between approaching atoms, bond length, and bond energy, and state the octet rule. Chapter 6, Section 2, Covalent Bonding and Molecular Compounds. Many chemical compounds, including most of the chemicals that are in living things and are produced by living things, are composed of molecules. A molecule is a neutral group of atoms that are held together by covalent bonds. A single molecule of a chemical compound is an individual unit capable of existing on its own. It may consist of two or more atoms of the same element, as in oxygen, or two or more different atoms, as in water or sugar. See figure 6-4 on the screen now. A chemical compound whose simplest units are molecules is called a molecular compound. The composition of a compound is given by its chemical formula. A chemical formula indicates the relative numbers of atoms of each kind in a chemical compound by using the atomic symbols and numerical subscripts. The chemical formula of a molecular compound is referred to as a molecular formula. A molecular formula shows the types and numbers of atoms combined in a single molecule of a molecular compound. The molecular formula for water, for example, is H2O, which reflects the fact that a single water molecule consists of one oxygen atom joined by separate covalent bonds to two hydrogen atoms. A molecule of oxygen, O2, is an example of a diatomic molecule. A diatomic molecule is a molecule containing only two atoms. Formation of a covalent bond. As you read in Section 1, nature favors chemical bonding because most atoms are at lower potential energies when bonded to other atoms than they are as independent particles. In the case of covalent bond formation, this idea is illustrated by a simple example, the formation of a hydrogen-hydrogen bond. Picture the two isolated hydrogen atoms separated by a great distance, a distance large enough to prevent them from ever influencing each other. At this distance, the overall potential energy of the atoms is arbitrarily set to 0, as is shown in Part A of Figure 6-5 on page 165 of your text or on the screen now. Now consider what happens if the hydrogen atoms approach each other. Each atom has a nucleus containing a single positively charged proton. The nucleus of each atom is surrounded by a negatively charged electron in a spherical 1s orbital. As the atoms near each other, their charged particles begin to interact, as shown in Figure 6-6 on page 165 of your text or on the screen now. The approaching nuclei and the electrons are attracted to each other, which corresponds to a decrease in the total potential energy of the atoms. At the same time, the two nuclei repel each other and the two electrons repel each other, which results in an increase in potential energy. The relative strength of attraction and repulsion between the charged particles depends on the distance separating the atoms. When the atoms first see each other, per se, the electron-proton attraction is stronger than the electron-electron and proton-proton repulsions. Thus, the atoms are drawn to each other and their potential energy is lowered, as is shown in Part B of Figure 6-5. The attractive force continues to dominate and the total potential energy continues to decrease until eventually a distance is reached at which the repulsion between the like charges equals the attraction of the opposite charges. This is shown in Part C of Figure 6-5. At this point, which is represented by the bottom of the valley in the curve, potential energy is at a minimum and a stable hydrogen molecule forms. A closer approach of the atoms, shown in Part D of Figure 6-5, results in a sharp rise in potential energy as repulsion becomes increasingly greater at that distance. Characteristics of a covalent bond. In figure 6-5, the bottom of the valley in the curve represents the balance between the attraction and repulsion in a stable covalent bond. At this point, the electrons of each hydrogen atom of the hydrogen molecule are shared between nuclei. As shown below in figure 6-7 on page 167 of your text, or on the screen now, the molecule's electrons can be pictured as occupying overlapping orbitals, moving about freely in either orbital. Therefore, each electron can feel the attraction of both nuclei. The result is an increase in electron density between the nuclei. The bonded atoms vibrate a bit, but as long as their potential energy remains close to the minimum, they are covalently bonded to each other. The distance between two bonded atoms at their minimum potential energy, that is, the average distance between the two bonded atoms, is the bond length. The bond length of a hydrogen-hydrogen bond is 75 picometers. In forming a covalent bond, the hydrogen atoms need to release energy as they change from isolated individual atoms to parts of a molecule. The amount of energy released equals the difference between the potential energy at the zero level, which are the separated atoms, and that at the bottom of the valley, the bonded atoms, as is represented in figure 6-5. The same amount of energy must be added to separate the bonded atoms. Bond energy is the energy required to break a chemical bond and form neutral isolated atoms. Scientists usually report bond energies in kilojoules per mole, which indicates the energy required to break 1 mole of bonds in isolated molecules. For example, 436 kilojoules of energy is needed to break the hydrogen-hydrogen bonds in 1 mole of hydrogen molecules and form 2 moles of separated hydrogen atoms.
Chemical bonds form when reacting atoms reach a lower potential energy when bonded than those same atoms would have as independent particles. In forming a covalent bond, electrons are shared and energy is released. The same amount of energy is needed to break them apart. This is called the bond energy. Bond energy varies with different kinds of atoms, as shown in this table.
The energy relationships described here for the formation of a hydrogen-hydrogen bond apply generally to all covalent bonds. However, bond lengths and bond energies vary with the types of atoms that have combined. Even the energy of a bond between the same two types of atoms varies somewhat depending on what other bonds the atoms have formed. These facts should be considered in examining the data in Table 6-1 on Table 168 of your text or on the screen now. The first 3 columns in the table list bonds, bond lengths, and bond energies of atoms in specific diatomic molecules. The last 3 columns give average values for specified bonds in many different compounds. All individual hydrogen atoms contain a single unpaired electron in a 1s atomic orbital. When 2 hydrogen atoms form a molecule, they share electrons in a covalent bond. As is illustrated in figure 6-8 on page 168 of your text, or on the screen now, sharing electrons allows each atom in the hydrogen molecule to experience the effect of a stable electron configuration of helium, 1s2. This tendency for atoms to achieve noble gas configurations through covalent bonding extends beyond the simple case of the hydrogen molecule. The octet rule. Unlike other atoms, the noble gas atoms exist independently in nature. They possess a minimum of energy existing on their own because of their special stability found in their electron configurations. This stability results from the fact that, with the exception of helium and its 2 electrons in its completely filled outer shell, the noble gas atom's outer s and p orbitals are completely filled by a total of 8 electrons. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. Such bond formation follows the octet rule. Chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, has an octet of electrons in its highest occupied energy level. Let's examine how the bonding in a fluorine molecule illustrates the octet rule. An independent fluorine atom has 7 electrons in its highest energy level, configuration of 2s2, 2p5. Like hydrogen atoms, fluorine atoms bond covalently with each other to form diatomic molecules, F2. When 2 fluorine atoms bond, each atom shares one of its valence electrons with its partner. The shared electron pair effectively fills each atom's outermost energy level with an octet of electrons, as is illustrated in figure 6-9a on page 169 of your text or on the screen now. Figure 6-9b shows another example of the octet rule, in which the chlorine atom in a molecule of hydrogen chloride, HCl, achieves an outermost octet by sharing an electron pair with an atom of hydrogen.
The noble gas atoms are the only ones that exist readily in an isolated state in nature. The outer s and p orbitals of these elements are completely filled with electrons, 8 in most cases and 2 in the case of helium. As a result, these atoms have low potential energies and stable electron configurations. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. In this way, each atom has a stable noble gas type structure. Let's look at this same combination of atoms using orbital notation. If we join the unfilled orbitals of 2 atoms with a box, we see that the combination fills the orbital. There are, however, some exceptions to the octet rule. The most important ones relate to the elements hydrogen and boron. Hydrogen forms compounds to share a pair of electrons, filling its s orbital. Boron has only 3 valence electrons, and so forms compounds to share 6 electrons, filling its s and 2p orbitals.
Exceptions to the octet rule. Most main group elements tend to form covalent bonds according to the octet rule. However, there are exceptions. As you have seen, hydrogen forms bonds in which it is surrounded by only 2 electrons. Boron, B, has just 3 valence electrons, with a configuration of 2s2, 2p1. Because electron pairs are shared in covalent bonds, boron tends to form bonds in which it is surrounded by 6 electrons. In boron trifluoride, BF3, for example, the boron atom is surrounded by its own 3 valence electrons plus 1 from each of the 3 fluorine atoms bonded to it. Other atoms can be surrounded by more than 8 electrons when they combine with the highly electronegative elements fluorine, oxygen, and chlorine. In these cases of expanded valence, bonding involves electrons in the d orbitals as well as in the s and p orbitals. At this point, you should be able to define molecule and molecular formula, explain the relationships among potential energy, distance between approaching atoms, bond length, and bond energy, as well as state the octet rule.